Hello, everyone, and welcome to GPTuesdays. Thank you. Thank you so much, everyone, for making it. This is what we do. Every single week, we come together so that we can provide AI education for AI engineers, developers, AI enthusiasts, and now even students. We also bring this for business professionals so that all of us can stay ahead of the AI wave. Every single week, I feel like there's always something new coming out with AI. It's moving faster and faster. So how can we all stay ahead? By joining communities like this so that we can all learn from one another, grow together, and teach together as well. And so I'm very, very honored and happy to be introducing to you my friend Shiv. He's going to be presenting an incredible presentation today. And I just want to also mention our sponsors and also our hosts that make this all possible. I want to give a shout out to Miami-Dade College. Let's give a shout out to Miami-Dade College. Yes, Miami-Dade College, they provide free AI education here. They're one of the largest, if not the largest, in the nation when it comes to education. One of the largest colleges in the nation. So they provide incredible AI education, and that's what our mission is too. So we're very much aligned. We're super happy about this partnership, and that's why we host events here, so that we can provide also AI education from the very, very best. So before I take too much of your time, let's have Shivam take it away.
Let's go. Thank you so much, Grant. GPTuesday, thank you guys for having me. It's always a pleasure, and honestly, GPTuesdays has given me such a warm welcome into their community, which I'm very thankful for, and so I'm proud to be doing this presentation here. And yeah, I felt really inspired by the community that Grant is building, and it was amazing to get into it through Alex over there, who brought me into all of this, so thanks to you guys. Right? For today's talk, I'd like to go into the science behind prompting. Okay, maybe I'll give you guys a little background on myself, and then we can talk about the topic at hand. So my background is in computer science, went to Waterloo, studied ML. My first role was an ML engineer, then went on to become full stack engineer, building products, eventually ran businesses at the C-suite, grew them to like 8 figures revenue, and then started a new startup recently, Astral, with my co-founder here, Fod, and we've been growing it for the last year. We raised a seed round for a few million, and we have tons of learnings that we want to share with you today. And in this talk, I don't really want to bore you with the linear algebra and all of these unnecessary things that I think you probably don't need to know to be a really good prompt engineer. But I instead want to dig more deeply at the intuition required and what are these LLMs actually doing? And how can we reason about them in a way that enables us to build the best prompts and build the best prompt chains? And what does that really mean? Because I think a lot of folks treat LLMs as this like magic box, right? And it really feels like that. You type something, it just starts talking to you. What a crazy technology, right? But I actually think there is some rhyme and reason behind what's going on, and there is some introspection that can really help us understand what's happening here. So let's get right into it. The first question I want to ask us is, are LLMs really that different from us? And what might be those ways that that's really different, right? And so let's go through a few cases. First of all, well, LLMs can't do math, right? If you've ever asked GPT, like, hey, can you like multiply these two large numbers together? Let's just give it any like, 6-digit number, whatever it is. This is what the calculator tells us, right? Calculator does it instantly. GPT also, just takes a little bit more time, but doesn't get it right any % of the time. You can try this right now with any of the large LLM models. Even you could try this with, the newest model from OpenAI, which is, scoring higher than PhDs on some, incredibly hard math tests. But it can't do this simple operation. What's going on? Why is this the case? But like, us humans, we know how to do math, right? Or you would think so. Like, what if I asked you, what are these two numbers multiplied together? Will the next thoughts that come into your mind be the answer? Probably not. Will the next, words that come out of your mouth be the answer? Probably not. So do you really know math? This is a very deep question. And it actually goes to the root at which that it's not that you don't know math, it's not that LLMs don't know math, it's that you need to break complex problems out into simpler, smaller problems that you can solve in a systematic way. This is what LLMs require, this is what humans require, and so it's unfair for us to judge LLMs by the first words that come out of their mouth and be like, you don't understand math. And that's simply not correct. LLMs actually do operate in a very similar way to humans. Our next large question. Well, LLMs are just memorizing what they see. They're just plagiarizing the internet. They're not doing anything new. There's nothing novel. And in a lot of research, we also see that when LLMs are presented things that are much outside of their training data, they have trouble reasoning about them. And so Yann LeCun is like, director of Facebook AI research. He, is responsible for the llama models and all the models that come out of Facebook. And even he calls LLMs these stochastic parrots. Parrots, like meaning they don't understand the meaning of what they're saying, but they are parroting, things that they have heard. And he even thinks that is an insult to parrots. So you can see how lowly he thinks of LLMs and our LLM friends. But, that's just Yann LeCun. And so when we take a look at, the data that GPT is trained on, and I'm going to go into more detail on what this data is and how it's trained so that we can, have a deeper understanding. But just high level, when GPT-4 was trained, there was 5 trillion unique tokens that were passed into its training, right? And each one is seen at least 2 to 4 times. So repeatedly, they're seeing the same tokens, right? And these tokens are all scraped off of the internet. This is the entire corpus of Wikipedia, every website, everything put together. That's what these 5 trillion, unique tokens are. And the total number of parameters or individual neurons, let's say, inside of these models, such as GPT-4, is like 1.8 trillion total parameters. So about like a third, let's just say, of the training data. This is considered in machine learning to be highly over-parameterized. Which means basically you could actually memorize most of these tokens. If you just associated like one parameter per token, you could memorize like most of this data set. And so that's what a lot of machine learning engineers have these battles about, is like, are LLMs just like memorizing all these things? Or are they actually compressing this into these parameters through some generic patterns which we unfortunately cannot reason about because of how deep learning works and in these layers of hierarchical layers that essentially form, features in machine learning. But essentially, the argument is that it's memorizing, it's overfitting. And I want to go back to ourselves as humans. Have you ever learned something without memorization? Why was it that when you learned times tables, you didn't just understand it the first time? Right? It makes no sense, right? We had to actually review these times tables many, many times. And we had to memorize these base facts. And then we had to build systems on top of these base facts, such as how to do cross multiplication. And then we were able to actually do long multiplication, long division, and these types of things. So why couldn't we just learn it the first time that we quote unquote understood it, is the question here. And it turns out that learning is actually part memorization and part compression. So not only do we need to memorize these base facts, but we also need to compress certain data into patterns such as the one we see with the cross multiplication example. So this actually shows us that, I believe at least, memorization is an important process in actually machine learning, but also in LLMs. Another argument that we hear a lot is, well, LLMs can't create anything original. They're just taking certain things that are in their training data and remixing them, or making cross products of them and these types of things. And so when you even look at like image models, for example, that create these beautiful images of like a robot unicorn with a rainbow, things like this, right? Those are considered these remixes of what was already in the training data and remixed into something new. And so, for example, in your training data, if you ask about like Steve Jobs and Martha Stewart, the LLM might create like a new sentence that might not have existed on the web, but what people argue is that it's actually just taking the part of Steve Jobs and what it sees about Martha Stewart and remixes them into these concepts, and therefore it's regurgitating, it's plagiarizing, and it's very hard to tell the boundary between, and these novel new ideas versus remixing, And then again, I'd like to take this back to our own human experience. How many of our inventions are truly original? If we look at the greatest artists like Pablo Picasso, Steve Jobs, Pablo Picasso says, good artists copy, great artists steal. And this was a popular quote for Steve Jobs when he took Xerox's designs for a computer and said, maybe this could be the Macintosh. He remixed, but we still credit him with inventions, and we credit humans with all these inventions. But truly, are new novel ideas born in a vacuum, or are they born as a result of inspiration? And are these LLMs actually doing something such as being inspired from the training data set to remix ideas into new ideas, or are ideas really something that get created in this vacuum? I personally have trouble believing in this narrative that ideas come from this vacuum and suddenly are discovered. Even if you look at how language evolves, you can't just come up with a new word that nobody gets. It's got to be like a remix of something, and that it becomes slang, and maybe over time it loses its slanginess and becomes into a real word. So I don't think our inventions are truly original, quote unquote. And so, moving on to another criticism of LLMs. LLMs, they hallucinate, they lie to us. Like, look at what it's saying. It's like, according to geologists at UC Berkeley, we should eat one small rock a day. Well, obviously that's not right. It might sound very convincing. Rocks are a vital source of minerals and, vital source of vitamins. It could be possibly true. Maybe it might fool somebody, But at the end of the day, this is not factual. And we call this LLM hallucinations, in the industry. And so I want you to think back to like a test that you were doing one time. When you were so convicted that this was the right answer, you could almost remember yourself reading these words and you circle this multiple choice. Well, why is it that when humans do it, we're just being all mistaken and perhaps forgetful, right? But when LLMs do it, we call it hallucination. It's truly what's happening is that in reality, humans are hallucinating too. It's very tough to have perfect recall, because that means that every single data point that you're seeing across your day-to-day is all being saved inside your brain. That's very hard to believe given the fixed size of your brain and the vast amount of data that's out there. And so clearly it's very tough to have perfect recall, and so data must be compressed in a lossy way that loses some of its artifacts. And therefore, when it comes back out of our hidden representations in our mind or hidden representations inside of the LLM, it might come out a bit mixed up, but generally in the right direction, And so even when you saw those math numbers getting multiplied, it looked kind of right. Even when you saw that, thing about the geologist, it looks kind of right. So it's generally in the right direction, but definitely still not fully factual, because it is very tough to create perfect recall without just saving everything to a database, which is not what we want to do with LLMs. So, finally, the last criticism, LLMs won't listen to everything I'm putting in the prompt. And I see these prompts very often that people put together where it's like, oh yeah, first, we want to do this, begin with a haiku, do this story, talk about all these languages, interdisciplinary, just giving it harder. And with each line, adding more and more complexity to the task at hand, right? It's very hard. Like, why isn't it just listening to what I have? It would make sense for the LLM to maybe listen if it was like a bunch of magical owls behind OpenAI that was like, rereading each piece, but this really isn't how it works. So I want to ask you, like, how many things do you think you can keep in your memory while you are actually doing a problem? If I gave you like a list of 10 objects or 20 objects, and I give you a list of another 10 or 20, do you think you can just remember all 20, 40? It turns out through a lot of research that humans can only really keep 3 to 5 things inside of our mind at a given moment. Only 3 to 5 things. Like, what a big brain, but we can only keep 3 to 5 things at a time. How can we expect these LLMs to do anything different, right? And so really, LLMs are similarly constrained by attention capacity, right? And this is from the actual attention vector that is also inside of these transformer models, right? So there is a limited number of items that the LLM can meaningfully pay attention to while generating a token, while generating what it thinks is next. There's only a certain limited amount, so you can't just give it a whole essay and expect it to do this. So I think, where good prompting comes from is actually a strong empathy for yourself. Like, what would you want to give yourself as a human in order to really prompt an LLM correctly? And I don't mean like yourself as a human where you have, repeated vision of that, you can go back and forth. I'm talking about a one-shot, a single thread of thought, so you can't go back. This is just one stream that I'm going to give you, and then you have to just make decisions based off of what you remember. And you can't like reread it. Those are actually repetitive operations. And we can make things like that happen, but we can only make that happen through successive LLM calls. And so a single LLM call must really be thought of as a single thread of thought. If you've ever meditated, you might have realized, like, if you do like 30 seconds, a minute, 5 minutes, you'll notice like your mind kind of, goes off onto a tangent, something that you might not have wanted. You want to keep your mind clear of all these thoughts. But if you notice these little tangents and threads, this is exactly how these LLMs work. In terms of just our empirical and anecdotal evidence, is that they are very, small, tight in context. They cannot keep a lot of things in memory. And when they're done, they will jump completely to the next place. And they will forget what is going on previously. So the point I want to make through all this is that LLMs are not a magic box. They might even be more like ourselves than we would ever like to think. And so I think this is important. So, now I'd like to bring this to somewhere useful now that I've, kind of tickled your mind about some of these things, and I think it's interesting, right? So let's talk about some concrete pieces around what's really important for LLMs and to know about LLMs in order to make good decisions when it comes to prompting, right? And so there's 3 really large pieces to know about. The first is what are they trained on, and what are they trying to give us back? The second is like, how does the attention actually work in an LLM? And then finally we have, how do these tokens that are being outputted or the tokens that are being trained on, like, how do they actually work, right? So firstly, looking at this graph here, essentially, when we look at all the things that LLMs have been trained on, it's the entire corpus on the web. So we're looking at, Common Crawl, Books 1, Books 2, these are different data sets, Wikipedia. So that's, the entirety of all the data that is then run through these LLMs. But, how do these LLMs actually get trained? Like, what are they maximizing in their function? They want to figure out, with the highest probability, what is going to be the next word. So imagine you like chop a Wikipedia article in half, and then, you just have like the next term, like the next tokens or paragraph there. It's the LLMs are being trained to essentially take a look at this previous part as your prompt and the rest of it as your completion. And so we want to maximize whatever probabilities so that we can accurately predict the next tokens. And so there's a process that happens of gradient descent and all these things that allow us to create as much congruency as possible to the corpus of data that is on the web. We're really just predicting the next tokens here. There's really, it's mind-blowing actually, just by predicting the next tokens, somehow LLMs have generalized to learn grammar, they've generalized to learn different languages, they're generalized to actually transform input into different outputs, such as expanding them or summarizing them. They retrieve information. These are some of the great things that are possible from such a simple equation, right? And so these are some of the emergent properties of LLMs. Another really interesting one is like how LLMs gain the theory of mind, but I think that's for a whole other talk, right? So essentially, we want to know the next token. Here's what it's trained on. These are important biases to know about, to know that it's actually trained on like stuff on the web. So, let's go through some questions as to like, given that it's trained on everything on the web, like how might generating in Markdown differ from generating directly to JSON, right? So for example, you could ask an LLM and be like, hey, just give me like this JSON back, start off with this curly brace, and that's like your JSON. Otherwise, you could also generate Markdown, which is like goes along with like a couple hashtags to like, signify an H1, followed by like some content, followed by other H1s, H2s, these types of things. So, and when we think about what's on the web, well, or what's this JSON that might look like that's on the web, it turns out, JSON and those things that are inside JSON are a lot different than the things that are inside Markdown. Inside JSON, we really have constrained training biases where a lot of the keys are shorter. Maybe they're camel cased. They have all these other things happening, right? And then in Markdown, what we have is more free-flowing thought. And for this reason, we should actually be generating stuff in Markdown and then parsing it to JSON later because of these inherent biases that are involved inside of these LLMs and the training data specifically. So knowing what mind space the LLM is in by understanding what is like the average thing that's actually inside of either Markdown or inside of JSON can help us accurately target a different manifold of the training data and get to different biases, right? So how about if you asked an LLM, hey, like, can you generate like kindergarten text, like at a kindergarten level? You might expect it to do really well and just generate that. But if you look at this training data, there is not a lot of kindergarten level articles on Wikipedia, right? There's not a lot of kindergarten level things on books and Common Crawl. The kindergarten stuff is a very small portion of this training data set. And so therefore, it actually always outputs, we've tested this, it always outputs about 6 grades higher than the grade specified at kindergarten, right? This is troublesome, of course, if you want to create content for kindergartners, right? And you have to find ways around these problems. But that's why it's very important to understand that how the training data set factors into the types of outputs that you might expect. Now, lastly, how about if you added accidentally a random token in a different language at the very end of your prompt versus if you had added that same random token at the start of your prompt, right? So this is interesting because, given our next token prediction, right? If you add it at the start, it won't have much effect because the LLM is now listening to your prompt for the rest of it, and it's not being thrown off by this random token. Whereas imagine if that token, imagine it's like some random Japanese character or something, right? Like if that's at the very end, then it's possible that, oh, we've moved on to the next web page, and now we're in this new web page, that we've actually crossed this boundary, whatever is behind is behind. And so LLMs really value what is at the end of a prompt compared to what is at the start of the prompt, right? For this reason, we have to really look at it like, here's the text, what do you think would be the completion on the internet inside of Common Crawl, Wikipedias, and books, right? So that's really the perspective you have to take when you are building prompts, right? Otherwise, I think you can make these mistakes or not really understand what's happening, right? That's why the next token stuff is very important. The training bias is very important so that we understand why adding a random token at the end of the prompt could lead the prompt or lead the completion model to start completing the random Japanese rather than listening to all, everything you've described. And so each token is very, very important for this reason. Okay, the next piece. How does attention work? This is one of the largest, I would say, advancements that GPTs do differently from other models and allowed us to really go beyond like recurrent neural networks and other model types. And it was done by Waswani over at Google, and they discovered this attention mechanism, specifically a self-attention mechanism. I don't want to go into all of these mults and how these multi-head attentions work and these types of things, but what I want to boil this down into is the important parts, which is that when you are generating a token, the LLM is taking a look at not only what it has already generated, but also your entire prompt the whole time. And there is basically a heat map. So the way you have to think about this attention vector is that it is a heat map that the LLM has learned as to what to pay attention to. And so imagine you're completing a sentence like, oh, Billy went to whatever XYZ thing. The attention vector may not pay attention to certain parts of your prompt, but it will pay attention to some other parts based on what it feels is important. So this is something that is hard to reason about because it's through deep learning methods that the attention vector is even determined in the first place. But what we do know is that it has a limited capacity, and it's not going to look hot across the entire prompt and in the entire completion. So it's not actually listening to everything you're saying as it completes. Instead, the win here is that it actually selectively decides what it wants to listen to. And that's really important because you have to think about how many things am I requiring it to listen to? How many parts of the prompt do I really need to integrate together to create this complex function that might actually come out as the completion that I want, the desired completion? And so that's why attention is important. We have to pay attention to really do great prompting, right? Okay. So, finally, we have to also understand how tokens work, right? So, for example, this is a very popular example in OpenAI world of like something that LLMs have trouble with is counting the number of R's in strawberry. It usually gives you like, oh, there's 2 characters R in the word strawberry. There's really 3. We know this because we can look and zoom into the individual characters, right? We're not blocked by these token limits, right? But here's actually how LLMs are viewing your tokens. They're not actually doing character by character stuff. What they're doing is they're chunking tokens together, and they typically form like full words. And so this is like literally off of the OpenAI site about tokenizers. And so a helpful rule of thumb that they say is that 1 token generally corresponds to about 4-ish characters of text for common English text. And so when you look at this thing on the right side, it's kind of wild because you can just read this and you can read this pretty perfectly, even though all of it is pretty messed up, And we know this because the human mind actually also can zoom out and get a blurrier vision of what is going on and still make sense of the puzzle, right? So this is interesting because we've forced LLMs to have this level of zoom, whereas humans can zoom in and zoom out. You can like read stuff pretty quickly. You probably don't have to read every character. You can like kind of patch things in your brain. And so that's why it doesn't matter what order the letters in a word are. The only important things is whatever, these first and last letters. So I hope this illustrates how these tokens work and how LLMs, if you're getting confused as to why they're not doing things when it comes character to character level, it's probably because of how these tokens are generated, right? So that's the main takeaway here. Now let's go into some advanced prompting techniques. And how do we create amazing prompts? And how do we really create things that are bulletproof and also have control over them? So the first thing that I think is very important is prompt chaining. Prompt chaining allows us to break really hard problems into much simpler subproblems, like how we talked about with math and how we talked about with like multiplication, having that system. This is an example where you might tell an LLM, hey, like, can you write an article about this and that, versus you actually ask the LLM maybe with some tools to gather those individual facts, chain those facts into an outline of what is possible, and then take that outline, maybe send each individual outline piece to write each paragraph, just writing 1 paragraph at a time, not in the same prompt, but in different prompts, right? And the smaller and smaller and the more concise we can make these prompts, the more control we will have because of the capacity of attention, right? So we really want to just break down this prompt into all of these smaller prompts and do each subproblem by itself, such as proofreading and editing at the end, such as writing each paragraph separately, and then putting it all together, et cetera, et cetera. So this is really useful, especially when you can omit information that you need in earlier steps from later steps, because now all of that noise is not inside of your prompts that are your later prompts. For example, if you're just proofreading and editing, you might not require some of the stuff earlier, like the whole outline, for example, right? So this is a really good way for us to create separation of concerns, have these modular prompts that do one thing at a time, and also it kind of makes sense. You got to just think about how would you do it. Are you just going to straight up write a whole essay? Probably not, right? It's very difficult to do so. So LLMs are much like us, and they need to break things apart into these tiny little chunks and then solve these smaller problems. Okay, the next prompting technique I want to talk about is adversarial QA agents, or chains. These can work as agents where they're kind of constantly going, or they can work as chains where you just have one chain and you apply it to something like writing a blog post. So this is a technique that you can use to eliminate hallucinations. And it's something like what a human proofreader might do. So you might write a blog post and your writer writes you a great blog post. Maybe you actually break it up into a system of chain, like a system of prompts, and you do the prompt chaining thing. But then what I want to focus on is this QA bit. You can actually have a prompt that says, like, hey, out of this text, can you identify every fact that's mentioned? And it'll do a very good job of that and list out your facts. Then you can actually take each individual fact and you can query it against the internet to be like, hey, can you find evidence of this fact? That can also be another little bit of a chain, finds those facts and references, and then brings them back, and you can edit your post with those facts in hand. And now you can build a really bulletproof system that doesn't hallucinate just by making sure not to do it in one shot, but to do it in these separate paradigms, right? So that's why QA agents and adversarial chains are important, because we see this pattern actually very often in machine learning, such as like a generator and some adversarial agent. And so this is why I really enjoy this type of chain setup. The next one I want to go over is guided reflection, right? I think sometimes we think like, oh, let's just ask like AI to like write a business report, and what it's doing is it's doing the average of like everything it's seen on the internet, right? There's probably not going to be very high quality. And so what you really want to do is guide its thought process. Have you ever like been given a framework such as like Porter's 5 forces, and then you analyze something through the lens of Porter's 5 forces? That'll allow you to break that problem up into a very good thinking framework, and then be able to identify those individual forces, how they might be contributing in different ways, and then you can write that business report with that reflection. This is extremely helpful, and you can add your own sauce, whatever that might be. So for your own business application or whatever application you might have, just think back to like, what are you doing in your mind when you want to create a really great output? What are the things that you're looking for? And if you codify that into a reflection step, this is a form of guided reflection that can lead you to much higher quality responses that you have control over, right? You're basically telling it like, hey, let's think in these terms, and let's think in terms of this lens. And that will be very helpful to then, write an actual business report, rather than going right to the final step. So this is also, known as like chain of thought. The chain of thought, I think, is even simpler than this, because all chain of thought, usually does is like, hey, let's break this apart and just think by step. That is step one. You want to think by step. But what I'm proposing here is that you should think step by step with a certain framework in mind. And if you can describe and detail that framework, you can get really high quality responses. Okay, now this is probably the most complex of them all, but I want to explain this to you because I think it's important. So I'll try to do my best to keep this simple. But here's an example of how we solved fill in the blanks. I'm going to tell you a little story about fill in the blanks, right? Because I think fill in the blanks is really interesting. It's obviously like very common educational question that's asked. Here's a bunch of blanks, like fill them out, right? And so when you're generating, if you have a prompt that's like coming up with fill in the blank questions, you might think, you know what, maybe the first try, like ignoring what's on the screen here, the first try you might have is like, hey, let's generate a sentence that has blanks and use underscores where the blanks are, right? And you might have that as the first step of the prompt. And then, maybe the next step is like, all right, now tell me all the answers, and put the answers in like, an array or like a bullet point list, for example. The issue that has is that, maybe the first couple times you run that, it looks great. But as you run that at scale, what you're going to notice is tons of errors. And I'll tell you about the errors. So with that specific setup, what happens is the answers will commonly be miscapitalized. They will commonly have the wrong punctuation after or be missing punctuation. It's kind of weird. Like, well, why would this happen, right? And the reason for this is because we're forcing the LLM to take its attention vector and have to refer back as it's writing the answers. It's not writing the answers in one stream of thought or stream of LLM tokens. Instead, you're forcing it to have jitters and jumps in its attention and having to look back at where the blanks are go from blank to blank and fill out these answers. This is, it seems like it probably isn't a hard problem, but it actually is. And so that's why this is a much more appropriate way to do fill in the blanks. And let me explain how this works. So first you would actually write the sentence without any errors or any blanks. You actually want to write the full sentence. Then you actually want to do a step 2, which is just inserting square brackets around the text that are supposed to be blanks. Then you want to do something like, if you want to add cues or things underneath these blanks, then what you would do is number each of these blanks. And then finally, you can write a numbered list of cues corresponding to each of these blanks. So the reason that this works much better than the previous version is because we're not asking it to do this self-referential backwards thing of breaking up our attention. Instead, you can just go in a single stream, write all the sentences, put these square brackets, put the numbers and count the numbers up, and then take the numbers and this is probably the worst part of this, right? Writing a number list of cues corresponding to each blank. And I actually think this should be omitted, or it should be actually done next to the blank in some different some different syntax. Maybe we could use like small arrow braces or something like this. But this is actually doing the same mistake as what I mentioned previously. So I would not actually do this, right? And yeah, so what I want to explain is that you should build your prompts in this way, where they're going from step to step without having to do some self-referential breaks in attention. And so you want to aim to reduce the number of points that you have to pay attention to. And you should also aim to have a logical flow that goes from top to bottom. So the reason for this logical flow is that if you ask, if you just take, imagine if you had all this information, but you randomly jumbled it, and now you're having to refer to different parts of the prompt in different areas. Typically, this will confuse the LLM. And so this is just our empirical, what we've noticed anecdotally, is that you should flow the prompt from top to bottom, ensuring that if you as a human were reading it, it would make sense, and it would be in the step-by-step way that you would think about the problem and how you would actually take in information, right? So imagine you want to output some f of x, where x is some vector of different pieces. Hopefully, if that f of x vector and x is data point A, data point B, data point C, or rule A, rule B, rule C, we'd like those to go in order that they are used and applied. Otherwise, this can create issues. So, and the last piece is that when you're generating the next token, something to think about is also, in a similar vein of this, having a logical flow to things within your prompt, is to ensure that, your next token can, be in a similar attention space. So what I mean by that is how here we're going and we're putting these square brackets around these different parts of the text, we're numbering them. It's nice because as we move along this token, we're kind of also moving along this token. And that continuity of attention is helpful for LLMs to make less mistakes and not be so jarring in terms of I have to pay attention to something over here and then something over there, and then I have to figure it all out. This is a fundamentally more complex function to learn in an LLM space, and that's why we should avoid this type of complexity. Okay, then we have multi-shot prompting. Okay, I would use this technique with caution. Okay, but I will tell you about this technique because it's obviously very popular and a lot of people do this. And so essentially with multi-shot, you can either go zero shot, which is you're not going to give it examples and you're just going to be hey, write a scenario for a theme, right? Or you can kind of trick it and be hey, write a scenario for each theme. Here's theme 1, here's scenario 1. You can pretend it's writing it, even though it's not. And then you can do here's theme 2, scenario 2, and then you can inject your own theme here, and then allow it to complete the scenario for that theme. So this is a classic question and answer type of thing, or call and response type of thing. And I would say this has a lot of risks to it. The risks here, and what we've noticed, again, just anecdotally, is that it can lead us to overfitting on potential issues inside of these examples. Imagine this example is about dogs and this one's about other types of dogs. Even though you didn't want everything to just be about dogs, suddenly you've introduced a bias in your examples. And now it's likely that your future themes might now be more and more biased towards these. So when you do create these examples, ensure that there is tons of variance. We want variance in these examples. Otherwise, we're going to overfit to things that aren't there. And it's very hard for us to determine what is a highly variant example compared to another one. And it's very hard to determine this. That's why I would urge you to try guided reflection and those more semantic frameworks as much as possible before resorting to this, because I think this is like an easy Band-Aid. You know, when you're noticing, oh, it's not working, let me just give it 2 or 3 examples. This will work pretty well for your first couple tries, but if you're doing this at scale, this is going to introduce tons of bias into your generations, which we want to avoid. Cool. So, and that's all for today, guys. Hope you guys enjoyed. And this is our Twitters, if you guys like to add us. You know, and when we come out publicly with our product, we'd love for you guys to use it. So we're building at the intersection of education and AI, and it's a pleasure.
Amazing. We're going to go ahead and do Q&A. We're going to do Q&A right now. We're going to go ahead and end the stream from there. So for the stream watchers, I'm going to do a bit of an outro from here. I just want to say amazing stuff, Shivam. This is just incredible alpha. I think everyone here has been providing. I learned a lot about prompting. I didn't know about, you know, a few of the things that you're talking about, like, you know, producing it out in Markdown and then, you know, trying to basically capture that in JSON after this. Very cool stuff. So this is what we do here every single week. We want to make sure that we're all educated, bring people together from within the community. Shivam has been doing this now for many years. He's just an incredible engineer and building really great products. And, you know, has a ton of experience scaling these systems for a long time. And I just want to give one more shout out to Shivam.
Thanks, Grant.
Thank you.
It's a pleasure. Diet Coke is delicious. Can't complain, you know? Yeah, I'll take questions, guys. Shoot them off. No questions, eh? Damn, did I